Imagine yourself on the brink of an adventure that transcends time and space, where the laws of physics are the only ones that dictate the rules. I'm Paul Edward, and I'm about to be your guide on a journey that defies the imagination, exploring the history and future of the universe. But let me warn you, this is not going to be a smooth ride. Prepare to have your mind expanded to the point of questioning existence itself. Our saga begins at the beginning of everything, the Big Bang, that monumental event that took place 13.8 billion years ago, and which shaped every particle, every force, giving form to the universe as we know it. The expansion of the universe, as evidenced by physics, suggests that in an instant, everything was infinitely united, until something incredible happened. But what exactly started the Big Bang? And what happened in the brief moments that followed, when the laws of physics as we know them simply failed? In the first moments, when the universe was a boiling cauldron of pure energy, the fundamental forces were united, but how gravity became intertwined with the other forces remains one of the great enigmas. And here, dear traveler, we face our first big question. What shaped those first critical instants, and how did that shape the universe we know and inhabit? As the universe expanded and cooled, cosmic inflation occurred. Imagine the universe, the size of a single molecule, expanding at an unimaginable rate, reaching trillions of times its original size in the blink of an eye. And then the first particles appeared. Quarks, leptons, and their antiparticles intertwined as the universe continued its expansion and cooling, paving the way for the formation of the first atomic nuclei, protons and neutrons. In this primordial universe, matter slowly gained the upper hand over antimatter in a cosmic battle that would determine the composition of the cosmos. As the universe cooled, the first chemical elements began to form, with primordial nucleosynthesis taking place. During nucleosynthesis, the first chemical elements were created. Around 75% of what was formed was hydrogen, the simplest and lightest element. Another 25% was helium, a little heavier than hydrogen. Incredibly, these proportions of hydrogen and helium remain in the universe to this day, even inside stars. This is fascinating because it shows us that current observations of stars confirm theories about the beginnings of the universe. Elements heavier than helium, such as carbon, oxygen, and iron, were not formed in this initial process because they require even more extreme conditions, which can only be found inside stars or when they explode. And remember, all this happened quickly, in the first few minutes after the Big Bang. The universe continued to expand and cool, but it was still so hot that the electrons couldn't bond with the atomic nuclei to form neutral atoms. This created a state of plasma where nuclei and electrons were separated, and photons, particles of light, were trapped in this plasma, unable to move freely. This period is known as the Dark Ages because, despite all this heat and energy, the universe was dark. There was no visible light because the photons were trapped. About 310 years after the Big Bang, the universe finally cooled down enough so that electrons and nuclei could combine to form neutral atoms, mainly hydrogen. This allowed photons to escape, traveling freely through space. These photons form what we now call cosmic background radiation, a kind of luminous echo of the Big Bang, which we can still observe and which gives us clues as to what the universe was like at that time. From then on, small variations in the density of the universe began to cause matter to clump together, forming the first stars and galaxies. The interesting thing is that, in this chaotic beginning, these first stars were made up of practically only hydrogen and helium, and it was these that began to create the heavier elements when they died or exploded. Although there was light, photons, traveling through the universe, there was not yet a source of light, such as stars or quasars, that could illuminate space as we see it today. The universe was basically a large dark cloud and very homogeneous, meaning that matter was distributed fairly evenly throughout space. But there were some small differences in this distribution, some regions a little denser than others, caused by disturbances in the fabric of time and space just after the Big Bang. These small differences, or disturbances, grew as the universe expanded. Imagine them as little seeds that, over time, grew into denser areas of matter. These denser areas began to attract more matter, both visible matter, such as that which forms stars and planets, and dark matter, a form of matter that we can't see but know exists because it exerts gravity. In these denser regions, the first stars in the universe formed, known as population 3 stars. These stars were very different from the ones we see today. They were huge, very hot and bright, but had a relatively short lifespan because they burned their fuel, hydrogen and helium, very quickly. When these stars died, they helped form the heavier elements such as carbon, oxygen, and iron, spreading them throughout the universe. This is why we say that we are made of stardust, because the elements that make up our bodies and planet Earth originally came from these first stars. Those first stars and the dark matter around them formed the first galaxies, including the Milky Way, our own galaxy. It all started with those tiny differences in density in the early universe. The James Webb Space Telescope was created with several objectives, one of which is the possibility of observing very old stars that have never been seen before. In fact, in one of the first images that James Webb captured, called Deep Field, we were able to see very distant galaxies that formed shortly after the birth of the first stars. This period when the first stars appeared is known as the Age of Stars. However, about 4 billion years ago, something curious happened. The rate of expansion of the universe began to accelerate again. This probably happened because dark energy, a mysterious force that we are still trying to understand better, began to dominate the dynamics of the universe. Dark energy has an opposite effect to gravity. While gravity attracts objects in the universe, trying to pull them closer together, dark energy acts by pushing them further apart. This interplay of forces explains why some galaxies, such as the Milky Way and Andromeda, are getting closer to each other because they are relatively close and gravity is the dominant force between them, while the universe in general is expanding and galaxies are moving away from each other because of dark energy, which is more influential at greater distances. So what James Webb and other observations of the cosmos are showing us is a more complete picture of how the universe has evolved, from the formation of the first stars and galaxies to the role that dark energy plays today in the expansion of the universe. Modern telescopes, such as the James Webb, have been incredible in helping us understand more about the universe. But even with all this technology, we still have many unanswered questions. For example, 1. Origin of supermassive black holes. We don't know for sure how these giants of the universe came to be, or how they always end up in the center of galaxies. It's like a mystery. Who appeared first, the galaxy or the black hole in the middle of it? 2. Life of the stars. Although we know a lot about how stars live and die, there are still details, especially about the end of their lives, that we don't know. Each star has its own cycle, but what exactly happens at the final moment is still a little uncertain. 3. Exoplanets and life outside Earth. We are always looking for Earth-like planets because we want to know if there is life elsewhere in the universe. This search continues to be a great challenge, and we hope that telescopes like James Webb can give us more clues. Now, about our universe and the Age of Stars. This age began shortly after a period called the Age of Darkness, around 13.3 billion years ago, when the first stars began to shine. One more question arises. Are we at the beginning, the middle, or the end of this era? Will it last until the last star dies? Can you imagine a universe without any stars shining in the sky? When it comes to the lifespan of stars, especially red dwarfs, which are smaller and cooler, they have a very long lifespan, living up to trillions of years. This means that if one of these stars was born in the early stages of the universe, it is still out there, young and shining, having lived only a fraction of its total life. As time went by, something interesting happened. the amount of gas available to make new stars began to decrease. Furthermore, as more and more stars were created, they used up this gas and also produced new elements called metals by astronomers. In astronomy, metals are all the elements heavier than helium. These metals began to mix with the remaining gas, changing the recipe of the stars that would be formed next. This means that the stars being formed now are a little different from the first stars. They tend to be smaller and cooler because they have more of these metals in their composition. And over time, as the gas to form stars gets scarcer and scarcer, the production of new stars slows down. Scientists believe that eventually this gas will run out and the formation of new stars will stop. But there's no need to worry. It will take many, many billions of years for this to happen. Until then, we'll still have lots of stars forming, especially red dwarf stars, which are smaller, cooler, and live a long time, a few trillion years. We are living in a very special time in the universe, right at the beginning of the Age of Stars, when we can still see a sky full of bright stars and distant galaxies. If we were born in a few billion years' time, the night sky could be very different, perhaps even dark, without the stars and galaxies we can enjoy today. So the Age of Stars still has a long way to go, and we are in a privileged position to observe and appreciate all this beauty of the universe around us. Thank you very much for embarking on this adventure with me. See you next time.